Hi, my name is Dr. Levine, and this video will serve as an introduction to population models using differential equations. So I want to start with a motivating question. That is, how fast does an epidemic grow? So you can see here I have a simulation of an epidemic wherein I have 100 initially infected people, and each infected person causes on average one new infection per week. So I would like you to sort of put your intellectual chips on the table and make a guess, a real guess. How many total cases do you expect there to be after 1 week? So each of these 100 individuals is sort of wiggling around in this simulated space, and there are tons and tons and tons of uninfected people that they might cough upon and make sick. And on average, they will have one of those successful coughs once per week. So very seriously, pause the video and write down a guess. How many infections do you think there will be at the end of 1 week? Hey, seriously, do it. Pause the video. Okay, so at the end of this 1 week, what we actually observe is that there are, from the initially 100 infected people, at the end of the 7th day, at the end of the first week, there are 282 infected people. What I'm willing to guess is that very many of you very earnestly, and I think rightly, made the guess that if every of those 100 people creates one new infection per week, that I should expect a pure doubling, a proper doubling from 100 to 200. So all of these extra 82 infections are sort of somehow being missed by that, what we might call first order thinking. So let's hop into the iPad and see if we can understand where all of those extra infections are coming from. So here we are. I'm looking at this one simulated week, and I'm thinking of a single infected individual. So one single infected individual here has this timeline wherein they're wiggling about, and on any given day, they might or might not have a productive cough in the grocery store that results in someone else getting sick. And what I expect is over this 1 week, exactly one of those productive coughs will happen, right? I have what I might call a lambda of 1. So a lambda of 1 infection per week. But what I can see is that this person might find that it's on the 3rd day that they have this sort of productive infection event. And this infection then leads to, if this was infection number 1, this leads to a second infected person who now has their very own independent timeline wherein they might be causing new productive infections. So there are still several days left in this week where person number 2 now has the opportunity. There are now 2 individuals, individual number 1 and individual number 2, walking around potentially creating these infectious events. So if person number 2, on say the penultimate day of this week, themselves go and produce a new infection, I can imagine that by the end of the simulated week, it would not at all be unreasonable for there to be 3 infected individuals. This would not at all be an uncommon occurrence that one single infected individual ultimately downstream results in 3 infections within this first week, which is why maybe we can start getting a sense of why the 100 individuals way overshoot that doubling you might have predicted and give us this number around 280. Specifically, I might think to put some numbers to it. So if I think that y of t is going to be the number of infected individuals at time t, then at time 0, I know I have 100 people. And if I look at this timeline and break it down by days, so there's day 0, there's the end of the first week, and I break it up into these 7 days. then I might say if every infected person has on average one infection event per week, then it's maybe roughly a seventh of them that have that infectious event occur in the first day. So maybe we could say the probability or the proportion of people having an infectious event on that first day is roughly 1/7. So 1/7 of individuals cause a new infection each day. So by the end of the first day, which I might call y of 1/7, I'll have all of the 100 original people who were infected, plus 1/7 of them will have gone and caused a new infection. So plus 1/7 of those folks will have caused a new infection. So 1/7 of those 100 people will have gone and duplicated themselves. This number, I think, is about 114. On the second day, I now have 114 people walking about. So by the end of the second day, I will have had 114 people, 1/7 of them as well will have gone and replicated their own infection. They will have coughed on someone, right? Made someone else sick. By the end of the third day, by the way, this number I think comes out to be around 130. So now on the third day, I have 130 sick people going around, 1 plus 1/7 times 130. Notice here now, maybe it would be helpful to write this as 130 times 1 plus 1/7. Actually, if I think back to all of these time steps, all of these steps represent taking my current population and multiplying by 1 plus 1/7. So what is the 130? It's 114 times 1 plus 1/7 times 1 plus 1/7. And the 114 was 100 times 1 plus 1/7 times 1 plus 1/7 times 1 plus 1/7. So by the time I get to the end of the first week, I will have my 100 initial individuals, and every single day I will have multiplied that population by 1 1/7, 7 times for the 7 days in the week. And this ends us up with a number around like 254. At this point, this might be something a little familiar to you, right? This notion of 1 plus 1/7 to the 7th power. Of course, the fact that we've split this up into days and not into hours or minutes is completely arbitrary. So in general, I might expect that by the end of the first week, I would have 100 of my initial individuals that will have had infinitely many opportunities to infect other people, right? Say n opportunities. So 100 times 1 plus 1 over n to the n. And this is a great math fact, just a beautiful math fact. If it's not one you're familiar with, it's a great math fact. Is that if I take the limit as n approaches infinity of 1 plus 1 over n to the n, this is precisely the definition of E. This is precisely the definition of Euler's number E, which is a number sitting around 2.7. So where did all of those extra infections come from? They came from the fact that on the first day, some people got infected, and those new people then had the opportunity to go and create new infections themselves. So what do I expect? By the end of the first day, I don't have a doubling. At the end of the first week, I don't have a doubling as I might expect, but I have an equaling. So it's 100 times E, or roughly 272 infections. So I want to slap you with a definition now. And this is one of the most powerful ideas in mathematical biology. It's one of the sort of core tenets of using differential equations to model biological phenomena, and it's called a Poisson process. So definition, a Poisson process is a continuous random process where events occur randomly at a constant average rate, lambda. So I'm imagining that I have some timeline t, and I imagine that maybe each of these time intervals represents days or months or years. And that I have events occurring randomly, but at an average rate of lambda per unit time. So for instance, if lambda were 3, then I might imagine that maybe I have an event, roughly 3 events in the first time interval, maybe only 2 in the second, and then 4. Maybe we sneak in a 4th one there in the third time interval. So these could represent, for instance, earthquakes. So earthquakes are something that have not very strong correlated relationship with one another. They occur more or less randomly, but at a constant average rate. Or pandemics, for instance, or hurricanes making landfall on the Gulf Coast. Anything that happens sort of at a constant average rate, but there isn't a strong correlation between the waiting times between such events. So a key example would be if I'm an infected person carrying some disease and I'm going about, I don't expect to infect new people with some metronomic precision, but just sort of randomly here and there, I might expect to, on average, cause 1 new infection per week. But from instant to instant, there's sort of no correlation. So a key example, though, or how we might implement this in a biological model, would be to imagine a growing population. I like to use a cell colony or a yeast cell colony, a growing population of, say, yeast cells. And they divide at a rate of lambda divisions per week. Sorry, let's say that's not a reasonable time frame. Let's say per day. So I'm imagining that every single yeast cell has this little timeline. And here's, say, 1 unit of time from, say, 0 to 1. And maybe I can imagine breaking this. I can imagine breaking this timeline up into, say, n subintervals. Well, among these n subintervals, I know that on average lambda of them will contain a division event. So this is one little yeast cell. That's my yeast cell. And this yeast cell knows that on average in this one day, it'll divide lambda times. So there's maybe a lambda, there's a lambda, there's a lambda. So, okay, so it's got 3 divisions in there. So there's lambda of those divisions. So on average, I'm seeing that each time interval contains a division with probability p equals lambda over n. Right, lambda, the number of divisions, over n, the number of total subintervals. Or rather, if I see each of these time intervals as being delta t, each of those is of length 1 over n. So similarly, I could think of this p as being lambda times delta t. So if I hone in and I focus on one specific time interval, say this time interval right here from time t to time t plus delta t, then I'd like to do a little bit of analysis. So I've got a population, my population at time t, I can think of my population at time t plus delta t will be the population at time t plus the number of divisions that occurred. The number of the divisions that occur will be the probability of any individual cell dividing times the total population. So this is p times y of t. Well, because I argued that p, the probability of any individual cell dividing in that small time interval, is just lambda times delta t, I get an expression that looks like this. And when I see a function evaluated at t plus delta t, and the function evaluated at t, and a delta t, this feels like a derivative in the making. All of the components for a derivative are right here. So I'm very tempted to form a difference quotient out of this. And I solve, mathy, mathy, math. I can subtract y of t over to the left-hand side. I can divide both sides now by delta t. And now I have precisely a difference quotient equal lambda times y of t. This, of course, I hope we recognize, if I were to slap a sneaky little limit in front, would become precisely y prime equals lambda times y. So I have developed what we call the Malthusian growth law. That when I have individuals who are independently dividing at a per capita growth rate lambda, so this is the individuals reproductive rate. The number, lambda here, is the number of individual reproductive events that one member of the population will experience per unit time. I get y prime equal lambda y. And of course, this is a differential equation that we know and love. We know how to solve this differential equation. I'm asking, what function, when I take the derivative, do I get just lambda times itself? And of course, the solution is c e to the lambda t. c e to the lambda t. Now, the magic of this growth law is that nothing about our argument necessitated that lambda be a constant. So this is where the real power comes in. lambda, the rate at which each individual is reproducing, need not be constant. So for instance, I can imagine that lambda could depend on seasonality. I can imagine that lambda of t, it could be lambda of t. Lambda could be a function itself of time. The individual reproductive rate could depend on time. For instance, there could be a mating season and an off season. I could imagine that lambda could depend on crowding. I maybe have an environment that depends in which there's resource limitation, and individuals can reproduce less quickly the more crowding there is. So lambda could be a decreasing function of y. So let me conclude with this. This is my question to you. Can you give an example of a scenario where lambda is non-constant? Why is it non-constant? And what would lambda look like? As a function of t, or maybe of y itself. Some examples might be resource limitation. There's just not enough resources to support an infinitely growing cell colony. Or maybe there's an external factor like seasonality. Maybe the temperature varies with the season, and the ability of the colony to grow depends on its access to warmth. So come up with an example. Come up with an example. How might the birth rate depend on some external factor? Okay, that concludes this video. Thank you for your patience. I hope you watched it at 1.5 times speed.